Welcome back. Problem 9-37. This problem is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the shaft has a diameter d and is subjected to loading shown. Determine the principal stress and the maximum in plane shear stress that is developed at point A. The bearings only support vertical reaction. So you can see this is the shaft, and at this end and at this end we have bearing that only supports vertical reaction. There is a point load P at this point. The total length is L. So you have to find the principal stresses and maximum in plane shear stress at this point A. So sigma 1 and sigma 2 principal stresses and maximum in plane shear stress. So let's start with the solution. So what we will do is that first step is that when you remove this support, so you will be having a vertical reaction, and when you remove this support again you will be having the same reaction force. Let this is 0.1 and this is 0.2, so it will be reaction will be R1 and it will be R2. So we'll find this R1 and R2 by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about 0.1 is equal to 0 and taking the counterclockwise movement as positive. So about 0.1, the first movement is produced by this P load and perpendicular distance is this one L by 2, and this is producing clockwise, so it will be negative. So I will write it first that P into P multiplied by L by 2, and this will be negative. The second moment that is produced by this load will be R2, and perpendicular distance is total this L by 2 plus L by 2, which is L, and that is producing counterclockwise, so it will be positive. So again I will write it plus R2 into L is equal to 0. This force is not producing moment because this is passing through this point. R1 is also not producing, and this force is not producing any movement. So only this force and this force is producing movement. Now from here we will get minus PL by 2 plus R2 into L is equal to 0. So what we will get is that R2 into L will be equal to plus PL by 2. And when you divide L on both sides, so you will get R2 will be equal to P divided by 2. So this is the value of R2. Now we will find R1 by using another equation of equilibrium, is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So R1 is upward and R2 is upward and R3 P is downward. So R1 plus R2 minus P is equal to 0. So we do not know R1. So R1 will be equal to P minus R2. Again, P minus R2 is P by 2. So when you calculate it, you will get R1 will be also equal to P divided by 2. Okay. Now we have this R1 and R2. So what we will do is that if you cut this beam at any length, for example, if I cut it over here, section AA, and draw the free body diagram, so it will be like this. This is the beam or this is the beam. Let me erase it. Okay. So this is the beam. Clear? So this is point F. This is point 1 where F load is applied horizontal. Here we have R1 which is equal to P divided by 2. I will also write R1 is equal to P divided by 2. So when you cut it, you will be having a shear force which will be equal to V, and you will be having a moment, and as well as you will having a horizontal reaction force which will be equal to N. So we'll find this N, V, and M. So for that, I will apply sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So F is acting plus side and N is acting negative side. So F minus N will be equal to 0. So it means that F is equal to N. Clear? So F is equal to N. Uh, we will use undo. Okay. Now we will find this V. So for that I will apply equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So R1 which is acting upward, which is P by 2, minus this V which is acting downward is equal to 0. So from here you will get this V is equal to P divided by 2. Now we'll find this M. So for M, I will apply equation of equilibrium that sum of all moment about section AA is equal to 0. So this is section AA. Clear? And taking the counterclockwise movement as positive. So about this, the first movement will be this P divided by 2, and we let cut it at L by 2. So this distance will be L by 2. Clear? So first movement will be this P by 2 into L by 2, and this is producing clockwise, so it will be negative. And the second movement about this section AA will be this reaction movement, and this will be counterclockwise, so their sum must be equal to 0. So I will write P divided by 2 into L divided by 2. This is minus plus M is equal to 0. So what we will get is that this movement will be equal to PL over 4. Now you can see here that this is the case where we have axial load that is compressive, clear, and we have a moment as well, clear. So due to this moment, again you can see here we will have a bending. So your normal stress which is equal to, I will write normal stress which is equal to normal stress which is equal to sigma will be the combination of axial load which is P by A. In this case it is F. So I will write general formula. This is compressive, so P minus P by A plus minus the stress due to this bending moment. So this stress will be equal to M into C divided by I. Clear? Again, now what we will do is that we have this we will find the area and moment of inertia. So area will, we do not have the diameter, it's general, so it is given that the diameter is D. Clear? So area of circular shaft is pi by 2 D square. Clear? And the moment, second moment of inertia for this circular shaft is equal to pi by 4 C power 4, and C is radius, so radius is equal to diameter divided by 2, which is 4, or it can be also equal to pi by 4 D power 4. Okay, now we have these values, clear. So due to this moment we will have bending stress. Bending will be equal to M into C divided by I, clear. And due to this normal compressive force which is minus P by A. So you can just put the value over here. So sigma will be equal to minus P will be replaced by F because this is F force and that is compressive, divided by pi by 4 D pi by 2 pi by 4 D square. So this is also area is pi by 4 D square. Now you can see that here, due to this bending, this beam will bend like this. Due to bending, the beam will bend like this, and we will find the principal stress is at this point A, which is in lower side. So lower side is in tension and upper side is in compression. Clear? So here the stress will be positive. So this will be replaced with plus sign. So I will write it plus moment, and C is this radius from center to the outermost, divided by I. I is pi by 4, pi by 64. This is 64. D pi by 64 d power 4. Now if you simplify it, will be equal to minus 4f over pi d square plus this moment is again equal to pl over 4 into c is d divided by 2 divided by pi by 64 d power 4. So further simplify, minus 4f over pi d square, and that will be equal to plus this will be equal to PLD over 8 divided by pi by 64 d power 4. So further simplify it, 4f over pi d square plus 8 will cancel with this 8, so 8 will be pi by 8. So again this will be equal to 8 PL over pi d cube, that will be equal to sigma. So this sigma, if you take 4 over pi d square as common, so this will be left with minus f plus 2pl over 2pl over t. Clear? So we can rewrite it 4 over pi d square into 2pl over d minus f. So this is the normal stress. Now again, if you look at here, this is point A where you are interested to find out the bending stress. So this is your point A, and this is the neutral axis. Let me draw it. So if this is the shaft, if this is the shaft and this is the neutral axis, clear, and this is your point A. So you can see that point A is outer surface. So we know that shear stress is equal to V into QA divided by I into T. Here QA will be equal to Y dash bar into area. So this is the point A and there is no area over here. So QA will be equal to 0. So QA, I will write QA will be equal to 0. So it means that shear stress will be also equal to 0. Now we have only normal stress sigma and shear stress is 0. So if I draw a state of stress like this, clear? So the normal stress which is given as this one, that is positive. So let me draw it. This is the normal stress. There is no stress in y direction. So sigma is equal to sigma x, and that is equal to 4 over pi d square into 2pl over d minus f. And shear stress is equal, tau of xy is equal to 0. Also sigma y is equal to 0. So only we have sigma x over here. And if you recall it, and if you want to draw the Mohr circle, so you will need the coordinates sigma x comma tau of xy and sigma y comma tau of xy. So here you can see you have sigma x and tau of xy is 0, and these both are 0. So if you plot it, for example, if this is the sigma x comes out to be over here and y is tau of xy is 0, and if you draw the Mohr circle like this, clear? So you can see that this is the principal stress, where we have sigma 1 and sigma 2, which is this one. So here you can see that sigma 1 will be equal to sigma x, which is equal to 4 over pi d square into 2pl over d minus f. Clear? And sigma 2 is 0. So these are the principal stresses. Now we will find the maximum in plane shear stress. So in plane, maximum in plane shear stress is given by formula, that is sigma x minus sigma y divided by 2 whole square plus tau of xy square. So you can just put the value. Sigma x is 4 over pi d square into 2pl over d minus f whole square minus 0 divided by 2 whole square plus tau of xy, which is 0 square, and under the root. That will give you in plane shear stress, and that will be maximum in plane shear stress. Again, when you calculate, it will be equal to this will be again equal to 4 over pi d square into 2pl over d minus f whole square divided by 4 under the root. This will be included over here in square. So again you will see that you will get this square will cut with this, so you will be having and 2 will be outside. So again in downward we will having 2, and this will be equal to let me clear it. Square will be cancelled. 2 to 4, 2 will come out. This will be equal to 4 over pi d square into 2pl over d minus f. That is maximum in plane shear stress. And this 2 will cancel with 4, so it will be 2 into 2pl over d minus f divided by pi d square, which is the in plane shear stress. And that is the answer of our these questions. So this is the maximum in plane shear stress, and this is the principal stresses. And that was all about this problem 9-17. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 9-38 and 9-39, that is taken from chapter number 9, Stress Transformation, and book name is Mechanics of Materials by R.C. Hibbeler. So statement is a paper tube is formed by rolling a paper strip in a spiral and then gluing the edge together as shown. Determine the shear stress acting along the seam, which is at 30 degree from the vertical when the tube is subjected to an axial force of 10 Newton. The paper is 1 millimeter thick and the tube has an outer diameter of 30 millimeter. And in another problem, it is given that solve problem 9-38 for normal stress acting perpendicular to seam. So you can see this is the paper tube that is formed by rolling the paper strip in a spiral and then gluing. And there is a normal load, tensile load of 10 Newton is applied, and this is the seam. Clear? You can see this seam is acting 30 degree from this vertical. Clear? So you have to find the shear stress along this seam, and in this part we have to find the normal stress that is acting perpendicular to this seam. So let's start with the solution. So first step is that you can see that you have this normal load, which is tensile load. So due to this tensile load, we have stress which is equal to this force per unit area, So what will be the area of this tube? So area of tube is equal to pi by 4 d outer square, d naught outer square minus d inner square. So we have this tube like this. Clear? This is the outer dia, clear, which is given as 30 millimeter. Clear? This is the thickness, which is given as t is equal to 1 millimeter. So with this d inner will be equal to d naught minus 2 times of t. Clear? So 30 minus 2 will be equal to 28 millimeter. This is d inner. So we have this, we can find area. So area will be equal to pi by 4 d naught, which is 30 millimeter. So in meter it is equal to 0.03 whole square minus d inner is 28. So in meter it is 0.028 whole square. So this is the area. So when you put, you have sigma p is given as 10 Newton axial load. So 10 divided by pi by 4 into 0.03 square minus 0.028 square. So when you solve this, you will get this normal stress comes out to be 109.76 kilopascal. And if you treat this like a state of stress on that element, so you will be having only this normal stress, which is sigma, and that sigma is 109.76 kilopascal. Now we have been given that this seam is at 30 angle from this vertical axis. So let this axis is y and this is along x axis. So we are going to transform it. So if you take it 30-degree counterclockwise, so your new y axis will be like this one. Here this will be your new y dash, and similarly your x axis will, x dash will be new axis, and that will be 30-degree. So what we are going to find out the shear stress on this along this seam and the normal stress that is perpendicular to this seam along x dash direction. Okay, so for that you can see theta is 30-degree. So theta is equal to 30-degree, and that is counterclockwise, CCW counterclockwise. Here you can see you have sigma in x direction is 109.76, sigma y is 0 because there is no normal stress in y direction, and tau of xy is also 0, there is no shear stress. So what we will do is that we will take this theta is 30-degree counterclockwise in order to find the transform shear stress, and we have this formula tau of x dash y dash is equal to minus sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy cos of 2 theta. So just put the value minus 109.76 minus 0 divided by 2 into sine of theta is 30 degrees. So sine of 2 theta will be equal to 60 degrees. So sine of 60 degree plus tau of xy is equal to 0. So 0 into cos of 60 degree will be 0. And that will be transform shear stress. Again, when you calculate it, you will get tau of x dash y dash comes out to be minus 47.5 kPa. Clear? So this is the shear stress along this seam. So let me show you. This will be like in downward direction opposite to x dash y dash, and that is tau of x dash y dash, which is 47.5. I have removed the negative sign because it is opposite to this y dash. Now we'll find the normal stress along this x dash, which will be the answer of the part 9-39. So we know that the transform stress sigma x dash will be equal to sigma x dash 9-39. Sigma x dash is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos of 2 theta plus tau of xy sine of 2 theta. So put the value 109.76 is sigma x plus sigma y is 0 divided by 2 plus 109.76 minus 0 divided by 2 into cos of 60 degree plus tau of xy, which is 0 into sine of 60 degree. That will give you sigma x dash. So sigma x dash, when you calculate, will comes out to be 82.3 kilopascal. So this is the normal stress that will be act perpendicular to this seam. So this is positive, so this will be equal to your sigma x dash, which is 982.3 kilopascal. So shear stress along this seam will be equal to 47.5, and the normal stress that is acting perpendicular to this seam will be 82.3 kilopascal. And that was all about this problem 9-38 and 9-39. I hope you have enjoyed this video and you have learned from it. Those from which are new to my channel, then subscribe it and don't forget to hit the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 9-40, and that is taken from chapter number 9, Stress Transformation, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the wide flange beam is subjected to 50 kilonewton force. Determine the principal stress in the beam at point A located on the web at the bottom of upper flange. Although it is not very accurate, use the shear formula to calculate the shear stress. So you can see this is a cantilever beam that is acted upon by a 50 kilonewton force at this end, and the cross section of this beam is shown, that is I beam, clear. And from here you can see this is the flange, these two are flanges, clear, and this is what we call web. So you have been asked to find the principal stresses in the beam located on the web at the bottom of, this is the top of the flange and this is the bottom of the upper flange, and this is upper flange and this one is lower flange. So you have to find the principal stresses at this point A. So let's start with this solution. So first step is that we first find the state of stress at point A. So for that, if I cut this beam at point A and draw the free body diagram, so this is the beam, clear. This is point where there is a point load acts, and that point load is 50 kilonewton. That this length is 3 meter, okay. And when you cut it at this point, so there will be a shear force that will be acting upward, which is represented as V, and there will be a moment that is equal to M. Clear? So we will find this shear force V and moment M. So for shear force, we will apply sum of all forces along Y direction must be equal to 0, and upward force is taken as positive. So we can see V is acting upward and 50 kilonewton is acting downward. Their sum must be equal to 0. So it means that shear force is equal to 50 kilonewton. And the moment can be obtained by using equation sum of all moments. Let this was your 1 point, about point 1 is equal to 0, and taking the counterclockwise movement as positive. So you can see about point 1, this shear force is passing through it, so it is not producing movement. So this force is producing movement, and the perpendicular distance is this 3 meter, and this is clockwise, so it will be negative. The second movement about point 1 is this counterclockwise movement, which is the reaction movement. So their sum must be equal to 0. So m, which is counterclockwise positive, minus 50 into perpendicular distance 3 is equal to 0. So from here we will get this movement will be equal to 150 kilonewton into meter. Now here you can see that uh, we have a shear force V acting and we have external movement M acting. Clear? So let this is the x-axis. Clear? This is y-axis and this z-axis is out of plane. So your this movement is about z-axis. Clear? So due to this you will have a stress, bending stress in x direction. So I will choose another color. You will have a bending stress in x direction and this shear force will be along y direction. So if I draw the state of stress, clear, but before we will have sigma x, clear, which is not known yet, and we have a shear force which is given as 50 kilonewton. So we will calculate shear stress, which we also do not know. So what we will do, we'll find this sigma x, and we know that this sigma x is equal to m into y divided by I, where m is the bending moment, which we have calculated over here. Y is distance from neutral axis till topmost. So if you see that this is the beam, so it's symmetrical about this axis. Clear? So y is the distance from neutral axis till the point where point A lies. So this is the distance. This distance is y. And this distance you can see it is equal to 250 millimeter divided by 2, which is equal to 125 millimeter. And this y is in term of meter is 0.125 meter. Now we have y as well. I can be obtained by I is the second moment of inertia, and for this I beam it is equal to, if we take this hole as 200 by this total length is 250 plus 12 plus 12, which is equal to 274. So this is 274 millimeter, while width is 200 millimeter. So if I take this whole box and find the moment of inertia and then subtract these two empty portion, so we will get the moment of inertia of this beam. So I will write moment of inertia is equal to, generally it is equal to 1 over 12 bh cube. So for here I will be equal to 1 over 12. B is its breadth, which is 200 millimeter, and meter it is equal to 0.2, and height is 274, so which is in meter is 0.274 whole cube, minus 1 over 12 into, you can see this height will be equal to 250 and this will be equal to 200 minus 10 divided by 2, which is equal to 95. So 95. So I will write its breadth is equal to 0.95 and height is 0.250 whole cube. And there are two empty portion. One is this one and other is this one. So I will multiply it with 2. So I will multiply it with 2. So it will be equal to 2 divided by 12. Clear? So when you calculate it, you will get the moment of inertia, and this I will be equal to 95.4512 into 10 raised to power minus 6 meter power 4. Now you have all these things, so you can find this sigma x. So sigma x is equal to moment, which is equal to 150 kilonewton. So kilonewton will be converted into newton into meter. Y is 0.125, clear, divided by I, which is equal to 95.45123 into 10 raised to power minus 6. So you will get sigma x will be equal to sigma x will be equal to 196.43 megapascal. and this stress is at point A. So we will get this is also equal to sigma A because it is calculated at this point A. Y is taken from neutral axis till point A. Okay. So we have sigma A is equal to 196.43 megapascal. Now we'll find shear stress. So we know that shearing stress is equal to V into Q divided by I into T. So for point A, it will be equal to shearing stress at point A will be equal to V into QA divided by I into T. So what is the Q? So you can see that we will find, since this point is here, so the above the point A, this area will be taken, and we know that QA is equal to y dash bar into A dash. So A dash is this area which I am going to shade. So this area is A dash. Its width is 200 millimeter and thickness is 12 millimeter. So first I will calculate A dash. A dash is equal to thickness which is 0.012 clear, and width is 0.20 meter, which is 200 millimeter clear, and y dash will be equal to distance from neutral axis till the mid of this section clear. So this is y dash, this is equal to y dash bar, and this is equal to this distance which is 0.125 and the half of this 12 millimeter. So it will be equal to this distance is 125 millimeter plus 6 millimeter. So it will be 131 millimeter y dash bar, and that is 0.131 meter. Okay, now you have the value, put it, y bar is 0.131 meter. So your QA will be equal to 0.131 multiplied by this area 0.012 into 0.200. So when you calculate it, you will get QA will be equal to 0.3144 into 10 raised to power minus 3 meter power cubic meter. Okay, now we have QAV is given as 50 kilonewton, which we have calculated at point A. We have QA I is also known this, and thickness. So this is the thickness. You can see this point A, and this thickness is 10 millimeter, which is 0.01. So thickness is equal to 10 millimeter, or it is equal to 0.010 meter. So you have all the value, put the value V is equal to 50 kilonewton. So 50 into 10 raised to power 3. Q is calculated as 0.3144 into 10 raised to power minus 3. I, which we have calculated, was 95.4512 into 10 raised to power minus 6, and thickness is 0.01. So when you calculate it, you will get shear stress at point A comes out to be 16.47 megapascal. Okay. So you can see this is the shear stress. Now we have here two stresses. One is normal stress in x direction, which is sigma A, and other one is shear stress, which is TA. So if you represent it on a state of stress, let's say this is an element at point A. So your normal stress, which is sigma A, is this one clear, and your shear stress is TA clear, and shear stress is TA. Okay, so if you represent this TA, so it will be like this. This is your shear stress on this face, which is equal to TA. There is no normal stress in y direction, so it will be 0. So from here you can see that you have sigma x is equal to sigma A, and that is equal to 196.43 megapascal. Clear? Sigma y, which is not available, and that is 0, and tau of xy is equal to shear stress at point A, which is equal to 16.47 megapascal. Okay, now we know that principal stress is sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. So just put the value sigma x is 196.43 plus 0 divided by 2 plus minus 196.43 minus 0 divided by 2 whole square plus 16.47 whole square, which is equal to sigma 1 comma 2. So again sigma 1 will be equal to 196.43 divided by 2 plus 196.43 divided by 2 whole square plus 16.47 whole square. And when you calculate it, you will get it 198 megapascal. Similarly, you can calculate sigma 2, and sigma 2 will be equal to 196.43 divided by 2 minus under the root 196.43 divided by 2 whole square plus 16.47 whole square. And when you calculate it, you will get minus 1.37 megapascal. So at the end, we have calculated the principal stresses, which are the maximum stresses at point A, is equal to 198 megapascal, and other principal stress is minus 1.37 megapascal. And that was all about this problem 9-40. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Also try problem 9-41, that is exactly same, but here the principal stresses will be at point B. So try it, and my next video will be about 9-41. Thank you. Welcome back. In our previous video, we solved problem 9-40, and in this video, we are going to solve problem 9-41, that is taken from chapter number 9, Stress Transformation, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the wide flange beam is subjected to 50 kilonewton load. Determine the principal stresses in the beam at point. Now here it is given that point B located on the web at the top of the bottom flange. So you can see this is the cantilever beam that is acted upon by 50 kilonewton load at this end, and the cross section of this beam is shown, that is I beam. So you have to find the principal stresses at the point B located on the web at the top of the bottom flange. So you can see this is bottom flange, this is top flange, this is web. So you have to find the principal stresses at point B. Clear? That is sigma 1 and sigma 2. So let's start with the solution. So first step is that we are going to find out the state of stress at point A. So for that we will cut the beam at point B, or at this section AA. Clear? And draw the free body diagram. So it will be like this. Clear? This is point where you have a point load of 50 kilonewton. Clear? This length, which is given as 3 meter. So when you cut it at section AA, clear, this is section AA. So you will be having a shear force in upward direction, which is equal to V, and you will be having a movement like this. So we will find this moment and shear force. So for shear force, we will apply the sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So two forces, one is V and 50 is acting. So V is upward, so it will be positive, minus 50 is downward. Their sum must be equal to 0. So it means that this shear force is equal to 50 kilo Newton. Now we'll find this moment. So for moment, we'll apply sum of all moment about section AA must be equal to 0, taking the counterclockwise moment as positive. So about this section AA, the one moment is due to this 50 kilonewton load into perpendicular distance is 3, and this is producing clockwise, so it will be negative. The second moment is this external moment, which is counterclockwise, so it will be positive. So their sum must be equal to 0. So I will write m minus 50 into 3 is equal to 0. So from here, this moment will be equal to 150 kilonewton into meter. Now you can see that here we have one shear force that is acting upward, clear, which is V, and we have a moment which is counterclockwise. So due to this moment, this is x-axis, this is its y-axis, clear, and this is the z-axis. So you can see this movement will be about z-axis, this movement, and the shear force that is acting downward will be in y direction. So due to this movement, the normal stress will be generated, or bending stress will be generated in this x direction, which is sigma x, clear. So we'll find this sigma x, and due to this shear force, we will be having a shear force. So what we will do is that we will find this sigma x, which is generally we are calculating at B, and due to shear force V, we will have shear stress. And since we are finding at B, so we will find this. So we know that sigma x, or sigma at point B, bending stress due to bending moment, is equal to moment into y divided by I, clear. So moment is 150 kilonewton into meter. So what is y? So y is again this symmetrical beam. If you take the mid axis of this beam, so y is distance from neutral axis till this point B. This is equal to y, and this y is downward, so it will be negative, and it will be equal to minus 250 divided by 2, which is equal to minus 0.125 meter. It will be equal to 125 millimeter. So in meter, it will be equal to this one. And what about I? So we will find I, which is section property, and that is equal to 1 over 12 BH cube. So B is this 200 and H is equal to this total is 274. So we will take this whole box and we will find the moment of inertia about this axis, and then we will subtract the moment of inertia of this remaining two. So it will give you the moment of inertia of this shaded portion. So 1 over 2, B is 200 millimeter, which is in meter is 0.200, and height is 274, which is 0.274, minus 2 times 1 over 12. B is equal to 95. You can see this is 200, so 200 minus 10 will be equal to 190, and 190 divided by 2 is 95 millimeter, which is 0.095. Okay. And height is 250, so it is equal to 0.250 whole cube. Now when you solve this, you will get the moment of inertia comes out to be 95.45123 into 10 raised to power minus 6 meter power 4. Now you have all the values. You can find sigma B is equal to m into yb divided by I. So moment is given as 150 kilonewton. So 150 into 10 raised to power 3, yb is minus 0.125, clear, divide by I, which is 95.45123 into 10 raised to power minus 6. So when you solve this, you will get this sigma B comes out to be minus 196.43 megapascal. So this is the normal stress or bending stress due to bending moment. Now we will find the shear stress at point B, which is equal to V QB divided by I into T. So we have shear force V is given as 50 kilonewton. Clear? I is again we have calculated 95.45123 into 10 raised to power minus 6. T is equal to, you can see this is the thickness. Let me show you, this is point B. So thickness is 10 millimeter and this 10 millimeter is equal to 0.010 meter. And what about QB? So QB will be equal to Y dash bar into A. And what is Y dash bar and what is A? So A is this area. This is the A. And this area is equal to 200 millimeter, which is 0.2 into thickness is 12 millimeter, which is 0.012. Clear? And what is Y dash bar? So Y dash bar is distance from neutral axis till the mid of this section. This is Y dash bar. And that is equal to, this distance is 125 plus this 12 divided by 2 is 6. So 125 plus 6 is equal to 131 millimeter. And this Y dash bar in meter is 0.131 meter. So I will write Y dash bar is 0.131 meter and A dash is 0.200 into thickness is 0.012. Okay. That is equal to QB. And when you solve this, this will be equal to 0.3144 into 10 raised to power minus 3 cubic meter. Now you have all the values, you can just put it, so you will get shear stress at point B is equal to shear force, which is 50 kilonewton, so 50 into 10 raised to power 3 multiplied by QB is 0.3144 into 10 raised to power minus 3 divided by I, which is 95.45123 into 10 raised to power minus 6 into T is 0.010. So when you calculate it, you will get shearing stress at point B comes out to be 16.47 megapascal. Okay. Now, if we draw the state of stress at point B, so let this is state of stress. This is the element. Clear? So you will having a in x direction you will have sigma B is negative, so it will be compressive. Clear? This is sigma B, which you can see that is minus 196.43, and you will be having a shear stress which is 16.47, so it will be like this. This is shearing stress at point B. Similarly, over this face it will be downward and this will be like this. Now you can see you have sigma x here is equal to sigma B, which is equal to minus 196.43 megapascal. Sigma y here is not available, so it will be equal to 0. And tau of xy, which is equal to shear stress at point B, is equal to 16.47 megapascal. Now principal stresses, we have to calculate principal stresses, and these principal stresses are the maximum stresses, which is equal to sigma 1 and sigma 2. And we know that sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus under the root sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. Now just put the value sigma 1 comma 2 is equal to minus 196.43 plus 0 divided by 2 plus minus under the root minus 196.43 minus 0 divided by 2 whole square plus 16.47 whole square, and all these are under the root. So for sigma 1 is equal to, it will be equal to minus 196.43 divided by 2 plus this 196.43 divided by 2 whole square plus 16.47 whole square. And when you calculate, it will be equal to 1.37 megapascal. Similarly, you can find sigma 2, which is equal to minus 196.43 divided by 2 minus 196.43 divided by 2 whole square plus 16.47 whole square under the root. And when you calculate it, it will be equal to minus 198 megapascal. So according to this, sigma 1 is 1.37 megapascal and sigma 2 is equal to minus 198 megapascal. So these are the principal stresses that is acting at point B due to the given loading. And that was all about this problem 9-41. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-42. This problem is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the drill pipe has an outer diameter of 3 inch and a wall thickness of 0.25 inch and weight of 50 pounds per feet. If it is subjected to torque and axial load as shown, determine the principal stresses, the maximum in plane shear stress at point on its surface at section AA. So you can see this is a drill pipe, clear, that is subjected to axial load as well as this torque, clear, and you have to find the principal stresses and maximum in plane shear at this section AA, clear. This pipe has a weight of 50 pounds per feet that will act downward. So let's start with the solution. So if you cut this pipe at section AA and draw the free body diagram, so it will be like this, that this is the pipe, this is the length at which we have cut this pipe, clear. This length is 20 feet, clear, and we have a load of 1500 pounds, clear, and we have a torque that is mentioned over here, that is 800 pounds into feet, and this length is 20 feet. So when you cut it, so definitely you will be having a reaction force which will be represented as N, and you will be having a resultant torque in this opposite direction. This will be the torque T. So we'll find this T and N. Also you can see the weight of this pipe is 50 pound per feet. So this length, for the length of 20 feet, so this weight will be also act downward, and this weight will be equal to 50 multiplied by 20, and the unit will be equal to 50 multiplied by 20 will be 10,000, and the unit will be pounds. Now we'll apply equation of equilibrium. That first equation of equilibrium is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force which is along y direction is 1500, that is downward. The other one is N, which is upward, and third one is this weight which is 1000 pounds, that is downward. So downward force is taken as negative. So minus 1500 plus 1000 minus 1000 minus 1000 plus this n which is upward is their sum must be equal to 0. So from here this reaction axial force will be equal to 2500 pounds. Now we'll find this resultant reaction torque. So for that I will apply equation of that sum of all movement, or you can say that this is the torque which is 800 pound into feet. So there is no other torque, and this torque reaction torque which is opposite to that. So this T will be equal to this T will be equal to this T will be equal to 800 pounds into feet, but that will be counterclock. If this is counterclockwise, so this will be clockwise. This T will be equal to clockwise. Now you can see you have a normal axial load and you have a torque. So if I draw the state of stress like this, let this is the element, clear. So due to this normal load, we have a normal force, and due to this torque, we have a shear force. So for normal load, I will write it. Normal load, we have normal stress which is equal to this load N divided by A, and for shear, for for torque we have, due to this torque we have a shear stress which is equal to T torque into C divided by J, where T is torque, C is the radius, and J is the polar moment of inertia. So first we will calculate it. So N is 2500, so 2500 divided by area. So area of this circular hollow pipe will be equal to pi by 4 d outer square. So d outer square, d outer is 3 inch, so 3 square minus d inner. So d inner, d outer is 3 inch, clear, and this is 0.25. So this also corrected, this is 0.25. So it means that d inner will be equal to d outer minus 2 time of thickness. So 3 minus 2 into 0.25 will give you d inner will be 2.5 inch. So I will write minus 2.5 whole square. So when you calculate it, you will get the normal stress comes out to be 1157.5 psi. Also you can see that this load is downward, this is also downward, and this is upward, so it will cause the compression. So compressive stress is taken as negative, so I will write minus sign with it. So this is compressive. So if you represent it on a state of element, so there is no stress in x direction, so sigma x will be equal to 0, and there in y direction this is compressive stress, so sigma y will be equal to this minus 1157.5 psi. So for shear stress we will calculate shear stress, and this shear stress is equal to torque which is equal to 800 pound into feet. So for converting it into inch we will multiply it with 12. So it will be 800 multiply by 12, and the unit will be pound into inch. Multiply by C. C is the radius. So maximum diameter is 3. So radius will be equal to 1.5. So I will multiply it with 1.5. Divide by J. J is the polar moment of inertia. And for circular hollow shaft or rod, it will be equal to pi by 2 C outer. C outer means radius outer, which is 1.5 power 4 minus C inner, and C inner is 1.25 power 4. So if this is the pipe, circular pipe, clear, and this is the center. So if this is C outer, which is 1.5, and this is the thickness, which is given as 0.25. So C inner will be equal to C outer minus thickness. So C outer is 1.5 minus thickness 0.25 will be equal to 1.25 inch. Clear? So when you calculate it, you will get the shear stress comes out to be 3497.5 psi. And if you represent it on a state of on this element, so it will be like this. This will be tau of xy, and here it will be like this. Clear? Now you can see that you have sigma x is equal to 0, sigma y is minus 1157.5 psi, and you have shear stress tau of x y will be 3497.5 psi. So for calculating the principal stresses, we know that principal stresses is sigma 1 comma 2, which is the first part, A part, and that is equal to sigma x plus sigma y divided by 2 plus minus under the root sigma x minus sigma y divided by 2 whole square plus tau of xy square. So put the value, we have 0 minus 1157.5 divided by 2 plus minus under the root 0 minus minus will be plus 1157.5 divided by 2 whole square plus 3497.5 square. Clear? That will give you sigma 1 comma sigma 2. So for finding sigma 1, so it will be equal to minus 578.75 plus, if you calculate this value comes out to be 3545.08, and when you add them you will get sigma 1 will be equal to 2966 psi, or in KSI it will be 2.97 KSI. Similarly, sigma 2 can be obtained by subtracting minus 578.75 minus 3545.08, and that will be equal to minus 4124 psi, or you can say 4.12 KSI, that will be minus. So these are the principal stresses. Sigma 1 is 2.97 KSI and sigma 2 is equal to minus 4.12 KSI. So these are the principal stresses which are the maximum stress that will act on this element, and that is the answer of our first part. In second part, we have been asked to find the maximum in plane shear stress, and we know that maximum in plane shear tau in plane maximum is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy square. So put the value, sigma x is 0 minus will be plus, and sigma y is 1157.5 divided by 2 whole square, and tau of xy which was 3497.5 whole square under the root. So you can see this is the same thing which have this value, and this in plane maximum shearing stress comes out to be 3545 psi, or in KSI it will be equal to 3.55 KSI. And this is the answer of our second part, which is the maximum in plane shear stress. And that was all about this problem 9-42. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.